Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we will discuss about the I/O parallelism. That means how to divide the data onto this I/O and we can provide the parallelism for accessing this disk. We will talk about the partitioning methods, what are the level of efficiency of each of the partitioning, and finally we will discuss about the skew and how we can handle the attribute skew, the partition skew to the histogram virtual processor techniques. Firstly, we will know that what is the levels of partitioning that we can have in I/O. That means if a total database is stored within a single disk, then the access rate for having an I/O to access that particular database is becoming high. But if we can divide the database into two different or three different parts on the disk of the database, then the access rate will be higher for that I/O. That means the faster I/O we can operate on that database. Say for we know that the database is stored and it is stored in a single one, but it is partitioned into two different ways, but in the single disk. That one section was consists the 0 to 50,000 salary, another is 50,000 to 1 lakh salary. So now even we want to know about the salary section of 60,000, we want to search for the total database in at all. Now this comes with the problem of this parallelism. That means now we are a concept arising with the parallelism where we can partition the data in such a way that it will be distributed among the disk, and we can partition in several methods based on the need of that particular partition. So after partitioning a data, we can parallelly access all the data items that belongs to the same database but different disks, so that we can increase the I/O fan out and also the time for this I/O operation. Now there are many methods to which we can partition the data, ranging from a particular limit or a condition or say sequentially. So we will describe each of this method elaboratively. First of all, we need to say that if there are n number of disks and we can produce d0 to dn minus 1 disk, that we can allocate this tuples. So n tuples need to be divided into d0 to dn minus number of disks. Now first the technique we will discuss is a round robin technique. We know that round robin technique just repeats the scans or repeats the steps itself after a fixed interval of time. Here it is I, that means for each tuple it will round it up. So now it first starts scanning at the beginning of the database and then it puts the ith tuple, say for the 0th tuple, it puts the data into the 0th disk. So the ith tuple goes to the dith of disk. The next one goes to the next disk. In this way, it puts all the di of tuple and this to di disk that the round robin method takes. Now what is the basic of this round robin method? That for each of the tuple is now storing at different types of disk. So obviously if we want to fetch in that type of data where the tuple is our important one, then we can have every information for the belonging to say employee, instructor or any other element have been done very easily. The next one is an attribute partitioning. Now when we are finding an hash partitioning or an attribute partitioning, first we scan the database at all. Then we need to find a particular attribute so that has the common value between all these tuples. We always have a common attribute that has the unique values to each of these tuples or sometimes the duplicate values to the tuples. Now after finding that particular attribute, which can be changed from one enterprise to another one. Say for the example that the basic attribute on which we want to partition can be a salary for the employee, but it can be a department for the instructor. So now depending on the relation and the need to partition will be my chosen of the attribute. Now after computing a good hash function, say hi onto this value, we will store the value on di mod I. That means on the block of di mod I disk, it will be placed the data of ith tuple. So on which this di mod I we have faced, that we are facing it with an hash partition. That means we have calculated the attributes hash value, and then we are using this hash value or the hash function as di mod I. We can use another functions also like the hash functions. The hash functions will be the later or the better partition that we can have. As we know, for the round robin, we can have an smooth and distribution of data that is even through all of the disk. Like for the first one, each of the disk will have the one tuple. If there are dn-1 and there are many tuples, then it will becomes with the second on the d0. That means after the nth tuple, again the n plus 1 tuple will come to the d0 disk. So in this way it will round it through this d0 to dn-1. So that is why the distribution is even. But if we are not choosing a good hash function, then we cannot choose an evenly distribution of the data inside an hash partitioning. Though it is not guaranteed that even for a very good hash partition, it is averagely distribution of even, but not guaranteed that every partition will have the same number of data, because we are using an hash function to compute the attribute, not in particular rounded method. The next is in range partition. Just like the hash partition where we are attribute hash valued it and then put the data inside the partition, we will now use in range to satisfy the range on that particular attribute and then put the relation or the tuple in that part of this disk. Say for an example that salary belongs to 0 to 50,000. So now we are maintaining one attribute, that is salary here, and then compare this salary as a range 0 to 50,000 for the first block, 50 to 90,000 for the second block, 90 to 1,50,000 for the third block, and so on. So for every associated disk we are having a range to it. That means for having a range that is di plus 1, if the value, say there is a vector partitioning or which we can choose v0 to vn-2, and if there is a value of attribute say a which is equals to x. Now if x is less than v0, then we will put x in d0. If x is better than v1, then we will put x in vi-1. Now if x is greater than vi plus less than vi plus 1, then we will put x in di plus 1. So in this way we can choose this partitioning on the basis of arranging. Say for an example, if there are 3 disks 0, 1, 2 and we have 3 ranges 5, 10 and 40. Say for the 0 to 5 we have the data stored in 0 disk, for the 5 to 40 we will have the 1 disk, and for above 40 we are having the third disk. So it is not always mandatory that the ranges will be even. The first one could be 0 to 5, next one could be 5 to 40, third one could be 40 or higher. So see, there is no evenness between the ranges, not even the partitions. So in this hash partitioning and range partitioning, we can see that there is no even distribution. However, to some extent, if we choose a good function, it will be an averagely even distribution for the hash partitioning. Now the next part is the comparison between these partitioning techniques. Now how to compare the partitioning techniques? Here we are mainly involved with an I/O operation. We know that all the data can be distributed parallelly and also can be accessed parallelly and simultaneously to each of the tuple at the same time. That means the first tuple and the nth tuple, we can access both the tuples at the same time without any delay to it. So now what we need to do, that we need to calculate the read time and the functional time of each of this I/O operation that is involved in this parallelism. And finally we can compute based on this time that which is the better one for me. Now to the general algorithm calculate for the comparison is, first we need to scan the entire database. That is true for all the cases. Now if it is some point queries, then the hash partitioning is better. That means, see, the department name is equal to physics. That means we are pointing to a part of this query. So now if any of the point that belongs to this pointer where the department name equals to physics, then we can go to the exact partition on the disk and find the partition around the tuples that belong to the partition. That means a hash function has been calculated on it, and we can support the point query by this point on the hash functions. Now what happens if we have the salary like this range queries? The range queries belong to the ranges on a query. That means now if the partition is done by a range partition, so it will be best supported by a range query where we can query upon say the salary 0 to 50,000, I want to find the instructor names. So now we can have for the instructor who is having the salary 0 to 50,000 supported by this range query or the range partitioning. Now the different type of partitioning has different types of level of efficiency that is associated with it. Now we will discuss about different types of association on efficiencies. The first one is in round robin. When we are talking about a round robin method, then we know that the round robin takes each of this data and put the tuple of that particular relation in each of the partition on the disk. Now as it suggests that to search the data sequentially or to read the data sequentially, it is absolutely useful for the round robin and it is efficient for that part only. Because if we want to go for a point query and range query, both of this is a complicated process for this round robin mechanism for partitioning, because we need to search all the n disk at the same time, but it will take a large number of IO fan out because all the disk IO we need to take for an n disk. Because now IO is having on the n disk, so it may be happen that one data is residing on one disk, at the last one we want to fetch. So with the round robin method, it is becoming absolutely complicated or impossible for us to reach this one. Now we will discuss about the hash partitioning. Now the next is the hash partitioning. In the hash partitioning, it is best supported for the point queries. Now we can say that we have chosen an attribute on a particular relation and use this attribute with a hash value that we can calculate a numerical value or any string value that is associated with that attribute. And from that index or the hash value, we can point to the data or make the partitions. That is the part of the hash partitioning. Now how it supports the point queries, say suppose that we want to find the telephone number which belongs to this range. Or we can say that not range when a particular telephone number we are maintaining. So it can happen that the office has a particular telephone number. Now all the employee that belongs to a particular office has this number. Now if it is for a single person or a single entity, then the good hash functions need to be chosen very carefully. Say suppose the telephone number is equals to 2555966. Obviously if it is not for an employee or the office details, then the telephone number can belong to only one person. That leads to store the data for one tuple in one disk, and it behaves like this round robin. But what happens if we know that for a department we are calculating the hash value, say for the department physics. So now there is some hash value to store all the tuples belongs to this department physics. So it can happen that there are 10 instructors belonging to the physics department, but only one instructor at the chemistry and 2 instructor at the maths department. So now the concept of skew arises where it is being sparse matrix or sparse partition, where we cannot have more than many data and one beta or the disk can be overflowed with it. Now we can say that the hash partition is better conditioned or supported with a point query expression or the efficiency. Now we can say that the point query is being supported by hash partition, and as well as sequential access is also good for the hash partition, because the hash value will give us a numerical result onto we can search for the value. Say for then a particular number or the name, if it is alphabetically sorted, then we can say that for each alphabetical sorting there is a number to it and we are storing the value associated to it. So now according to the number, it is better to go for a sequential search on that particular result. Now, if we can sequentially search with an hash partition, then we can see if there are n tuples, so we will need only 1 by n number of queries or 1 by n number of disk heads to IO operate on it. Now, the hash partitioning is not well suited for the non-partitioning queries. Say suppose if there is no partition on the query, we just want to group by the query and then have a result. Then hash functions is not well suited, and also it is not suited for the range queries, because for a range the hash function will not work, because now it is a range and it cannot compute for different values a single hash function. That will be a bad hash function. Now the next one is my range query or the range partitioning. So the range partitioning is best efficient for solving the range queries where we have a range on site and particular query, and the query partitioning can be done on it and we can store that particular range inside a query. Again, for the hash partitioning, it is not distributed evenly because one range can be overpopulated while the other range cannot have even one single item to it. So this range partitioning is suited for this range queries. Now, one advantage to have this range queries or the range partitioning is that if there is a lesser number of queries or the query on a range, then we can store it in a single disk rather than partitioning into different disks, which will increase then IO overhead or an overhead of keeping the data on Windex we need to keep. That will be less of a switch to a single disk store. Now the single disk store is only important or useful when we have different ranges within a shorter one. Now, if there is a search for a particular range of queries which is merged with another queries because they can store in a single disk or the small number, then there can be a bottleneck or the hot spare on which the execution is done. So this is also mentioned as execution skew. So what is an execution skew? It is known as at the time of executing a particular query, we are going to a single disk where there are number of range queries present to it, and now there is a bottleneck to which we need to execute the query. So as we introduce the term of execution skew, then we also need to introduce the term of skew first. So what is a skew? Before that, we need to know that for the hash partitioning and this range partitioning, not the round robin partitioning, it can happen that one partition is overflowed while other population is not populated. So what happens that one application or partition becomes skew in here. So the skew can be of two types. One is an attribution skew, another is an partition skew. So in the attribution skew, we have one attribute to which the hash value is calculated, and then we are storing the value against that attribute or against the range of that attribute. So in this type of problem, the attribute skew is overpopulated with some attributes and there is no value that is associated with another part of that attribute. Now the partition skew can, even if there is no attribute skew to it, that means only the attribute skew is not useful while we are having the partition skew. The problem mainly lies with the partitioning. So the attribute skew is generally the problem with this hash partitioning, whereas this partition skew is the problem with this range partitioning, where we need to create a range vector, and for which vector there will be a range of v0 to vn-2. Why n-2? Because there will be a range from n-1 to n-2 again, for which we are creating the partition. Now, if we need to choose over a particular partition and there are only a fewer number of disk blocks that is available inside the relation, so whether to have it in a single disk or to partition in it to a parallelism of IO, we can choose it in this way. Say suppose there are m disk blocks available onto the relation and n disks to be partitioned, then we can choose that we will partition the disk blocks in such a way so that we can reach minimum of m and n to the number of disks that we are partitioning. That means if m is lesser, that means we are having lesser number of disks, so we will have only m disk as the partitioning. And if it is n is lesser, then we need to divide m in such a way so that we can put it into n number of disks. Now what happens in this skew problem, that if we are having 1,000 entries and we are having only 100 partition to it, so on average there will be a 10 value to each of this partition. Now if one have the 40 number of partition in each of this, then we can have 25 number of this efficiency rather than having the 100. Now compare this situation if the same 1,000 number of tuples is divided into 10 number of skews. Now each of this proposed to have 1,000 on 100 number of skews. Now one partition has 200 number of skews, which will reduce the number of efficiency or the disk parallelism to 5, whether it was supposed to be 10. Now we can see that the reduced disk cost on this parallelism if it is not free from the skew. So we need to distribute it so much evenly as possible, because the hash partitioning to choose good, the range partitioning to belonging to a reasonable range, so that it can have an average even distribution between the relational data blocks. Now what happens to solve this skew problem? One solution is the balanced range query or the balanced range partitioning. What is an balanced range partitioning? First, based on this scanning on the algorithm and on the database, we first find the attribute on which the range is to be specified. Then we need to sort it down for that attribute. Now either for the point query or for the range partitioning, it is absolutely useful for having the partitions sorted down. That means if we have already sorted the initial partitions or the initial attribute, even now if we can put these ranges, then the data that will belong to and most even cases. Say for now we will have all the data that belongs to 0 to 50,000, and already that is being sorted down, so we can see that they are grouped together. So this is known as a balanced range partitioning, where we can sort the ranges and then make the partitioning based on these ranges. Now we can have an even number of data. Now even with a balanced range partitioning, we can arise in a situation where we are having that for a particular range there is an overpopulated data and other are not having any data at all. So this also be a problem, and this problem can be solved with the avoidance of an extra overhead of keeping the sorting. Now as we need an initial sort, so there is an overhead of the increased cost of this sorting. Say if it is in a large database, then to sort the initial one isn't very expensive. So to avoid this one and also the problem of balanced range partitioning, that we have an overpopulation on a particular range, can be solved with the histogram. Now if we put an histogram or sample an histogram from the data we have, then we can see from the histogram that what data is being used as the number of times and what data is being not used. So along with it, we can divide this partition in such a way so that we can have another attribute as the range. So other than having salary, we can have the department, or we can have any, say, the ages or the departments on which the histogram sets to have, and similar kind of height in this logical bars. Now if there are more ups and falls in this histogram, then it is specified that the partition will be one overpopulated and other one being skewed. So we can use this concept of histogram as to apply other than sorting it down, because it is more like sorting and we are only having the kind of histogram to it. Now say this example is showing you the histogram of 10 to 25, and we can store the data in 5 partitions where the data are ranging from somewhere high and somewhere low. Now another possible solution other than the histogram is that we are having the partition with this normal range and hash partitioning, not the round robin partitioning, because round robin partitioning gives us an even distribution in no matter what case it is, because after a particular time it will again repeat the scan and begin the n-1 with this n+1 number of tuples. Now what happens with a virtual processor? Say for an example that a single disk that we are using, and now we are considering that there are many processors that is attached to it. Now each of it is attached with a virtual concept. That means they are not physical processor but in memory area that is attached with single disk, and now we can have the partition which is overpopulated and have the virtual processor that is attached to it can divide it among the way. Now each of the virtual processor can divide the task so that we can have an even distribution, that is an apparent view on that particular disk. Now each of the partition is based on the range or hash partitioning, and now for each of the partition on the disk we are having attached one virtual processor which acts as a partition again. Now for each of this hash partitioning and this range partitioning, there will be some real-time processor on which the virtual processor will map this value to this real-time processor. For the round-robin processing, if we attach this virtual processor, this will be an extra overhead because already the data are being sorted and in an evenful distribution. Now for the hash and this round robin on this ranges partitioning, we can have the virtual processor, and then the round robin on this virtual processor will map the data to this real-time processor. So by this way we can manage the partitioning skew problem, the event distribution, the partitioning efficiency, and also the level of parallelism inside an I/O operation, that we can be faster inside several disks or and higher inside a single disk. So that is all for an I/O parallelism. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.